In software development and in computer science in general, we have a lot of problems to solve. Some people do that for the whole day. But when facing a problem, it may seem a bit abstract. This is why we need a way to represent it, to make it clearer and start thinking about a solution. For example, we want to suggest new friends to someone in a social media. For that, we decide to suggest friends of his friends. We have a list of connections between people. Who's friends with who? But to better visualize them, we can organize them this way. The circles represent people, and a connection between two circles means that those two people are friends. For example, red is a friend of gray. And from here, the problem becomes easy. We start from the person we want to suggest friends to, we check circles he's connected to, they represent his actual friends, and by checking adjacent circles of those circles, we can find friends of his friends. Another interesting example is this one. We want to travel between two cities, preferably by using the shortest path between them. For that, we have a list of cities and distances between them, and we need to find the shortest path. To better visualize the problem, we can organize data this way, where each circle represents a city, and the line between two cities means that we can move back and forth between them. The integer represents the distance. From here, we just apply an algorithm that we will learn about later to find the shortest path. We get this one for this example. Last example, we have a bunch of car rides to perform. We have the time when each ride starts and ends. However, we may not be able to realize them all with the same car, because some of them overlap in time. And the question is, what is the minimum number of cars to achieve them? We can visualize the car rides this way. Each circle represents a car ride, and the line between two rides means that they overlap. They can't be performed with the same car. Now to solve this problem, we can color the circles. Each color represents a car. But we don't color them anyhow. Remember that two adjacent rides means that they overlap. They can't be performed with the same car. In other words, they can't have the same color. So, to solve this problem, we will use an algorithm that we will learn about later to color the circles in a way that no two connected circles have the same color, by using as few different colors as possible. After doing so, the number of used colors represents the minimum number of required cars, 3 in this example. Okay, what's the common point between the 3 problem examples we've seen now? The common point is the structure we use to represent the problem. It's called a graph. A graph is simply a set of vertices that can be connected with edges. That's it. You can think of a graph as a network basically. Here is an example. But even with this simple concept, it remains a powerful tool that can be used to represent and solve a huge number of problems. It even has a whole branch of mathematics named graph theory. Graph theory is the study of graphs, the structure we define now. It has lemmas, theorems, conjectures, etc. But in this course, we will focus way more on graph theory algorithms, the algorithms that will give us the ability to solve problems by using graphs. For example, shortest path algorithms, graph coloring algorithms, minimum spanning tree algorithms, etc. And it's interesting to know how graph theory started. The first paper on graph theory appeared in 1736. It was written by Leonhard Euler. It solved the 7 bridges of Königsberg problem. The problem says that in the Königsberg's map at that time, we had 7 bridges as you can see. And the question is, can we find a path that traverses each of the 7 bridges exactly once? You can take some seconds to try. Swimming is not allowed obviously. Did you find one? I don't think so, because it's proven that such a path doesn't exist. But why? First of all, we can represent this map with a graph, where a vertex represents a region and an edge represents a bridge that connects 2 regions. And this graph has some properties that show that the path we're searching for doesn't exist. We will talk about that more in detail in the chapter about paths. Now we learned about what is a graph, some examples where we can apply it, but a lot of questions may come to your mind. Are there multiple types of graphs? Can a graph have no edges? Can we have multiple edges between the same two vertices? And many other ones. Those are interesting questions that will give us a better understanding of graphs. This is why in the next lecture, we will focus on the types of graphs and some terminology, to be more comfortable when we start discussing algorithms. See you in the next lecture.